Okay, so the uniqueness theorem in electromagnetics is one of the most important theorems in electromagnetics, maybe the most important theorem, because it says that as long as you follow a couple of caveats, you can, thank you, Andrew, smoke signals. We'll do smoke signals for office hours. I love it. The uniqueness theorem says that if I know the boundary conditions of a region in which I am trying to solve for field, then I can uniquely determine the field inside the bounded region that I know where the field boundary conditions are. That's good because it means that electromagnetic problems are actually solvable. Imagine there are lots of problems that have more than one solution to them. So formally, we define this as, okay, I have a region. It's bound by the surface, closed surface S. If I know the tangential E and H fields on this surface, what uniqueness says is that I can uniquely determine what the fields are inside that region, that volume bounded by surface S. And that's actually very important. You probably take that for granted. In previous electromagnetic classes, you just assumed there was a unique solution. You went about to solve it. And so we're going to show that that's actually, we're going to prove today that that's actually true. And we have to be very careful because there's a caveat involved. Again, this is one of those, if you dig down far enough into the muck, you'll find all the assumptions that all of your physical theory is based upon. And it's important to know when to apply and when that does not apply. So the way that we're going to do this, we're going to prove this by contradiction, or kind of like a contradiction. We're going to say, let's assume there are two solutions. There's E1 phasor and H1 phasor, an E and H pair that describe the field propagation inside the volume, and put a comma there. There's also an E2 phasor vector and an H2 phasor vector. Let's say there are two solutions, and then let's apply Maxwell's equation. So for example, Maxwell's equation said the curl of E1, let's do it this way. In my notes, one line I have them as A and B instead of 1 and 2. It's harmonized with the notes. Okay, E sub A, phasor vector. The curl of that first solution must be equal to minus J 2 pi F mu H in a homogeneous medium, and that's superscript A. And here's where you know you're dealing with a graduate level electromagnetics class, because we're going to add in magnetic current and phasor vector. These are magnetic charges, which you know don't exist, but it turns out that if you carry them along for the ride for a lot of electromagnetics problems, it is supremely valuable. It's a great analytical artifact for solving a lot of complicated problems, especially in scattering. So I'm just going to take them along for the ride, just to know, and I'm going to do the same thing for electric current, which doesn't exist, of course. We're going to do that so that we have a general framework for uniqueness that includes even the artifacts that we might want to introduce, like an impressed magnetic current. Now, of course, there are people that say, of course there's magnetic charge and a magnetic current, but it exists under the envelope of uncertainty. In other words, if you look at timescales down, picoseconds and femtoseconds or below, under the envelope of uncertainty, you could certainly have magnetic particles coming into existence and then popping back out of existence before you can witness them. That's neither here nor there. Just be aware that there are physicists out there that talk as such. So this is my first Maxwell's equation. I'm going to go ahead and just put the minus sign on the other end here. And my second solution must also satisfy this Maxwell's equation, which is really Faraday's law, right? These are the current sources inside. And I have a similar equation for Ampere's law, and with the Maxwellian correction factor, which says that the curl of my H phasor vector must be equal to J 2 pi F epsilon E plus J phasor vector, electric current plus basically the derivative of flux density. And that must be true for both the A and the B solutions if they are both truly to be solutions in that volume that contains epsilon, mu properties, as well as any impressed currents like J or M. Okay. Let's subtract these out. That's our next step. And so what we're going to do, this is a linear operator, so we're basically going to have, if I subtract this one from this one, I'm going to have minus the curl of what I'll call, it's going to be EA minus EB. But I'm going to call this delta E, the difference between the two solutions. And then I have J2 pi F mu E HA minus HB. And I'm going to call this delta H, the difference between these two solutions, A and B. And so what I have finally, what I'm left over is the curl of delta E is equal to J2 pi F mu delta H. And the common sources cancel out. The source is common to both solutions. We should be able to do the exact same thing here. We basically have delta H phasor. If I take the curl of that, that should give me J 2 pi F E delta E phasor vector. Common sources cancel. So this is our starting point for the uniqueness theorem. And the proof of it goes very straightforwardly. If I can show that delta E and delta H to be Maxwellian have to be equal to 0, then I've proved that these are the same solutions and there's only one unique solution to this particular problem that I've provided. Okay, so how do we go about doing that? So let's go ahead and apply an identity here. I'm going to dot, for example, I'm going to take this over here. I'm going to dot product delta H into both sides of these. In fact, it's going to be delta H complex conjugate. That's what this star is up here. I'm going to do that on both sides of this. So I basically have minus delta H. Yeah, make sure that you can see that down when I get out of the way. Okay, that's, the camera still picks that up. I'm trained to be thinking in terms of sight lines from the audience here. And normally if there were students in the room, they would have to kind of crane their necks over the podium here. We do not have that problem though. Dot it into the curl of this vector must be equal to j 2 pi f mu. Now, if I dot the complex conjugate vector into itself, what I really have is the normal. Delta H, phasor vector squared, magnitude squared, which of course is a positive number, which is very important for this proof. Likewise, I can do the same thing. If I dot dE complex conjugate into both sides of this one, I get dE phasor vector dotted into this phasor vector curl of dH is equal to j 2 pi f epsilon dE dotted into this dE gives you magnitude squared of my delta E vector. Okay, everybody follow so far? All I did is just make a new equation by dot producting both sides to produce these nice terms, which we know these are going to be positive values. Can't take the magnitude of the vector, no matter how complex it is, and still be a negative number. And that's one of the behaviors that we're going to rely on. So the next thing I'm going to do is I'm going to add these two behaviors together, or these two equations together. And add this one to this one. So let me go ahead and clear the board before we do that. Give myself some space to work. This is the part of the program where a more talented professor would be telling jokes and really corny stories. You know, I noticed that in the comments of some of the more recent videos, some of the students have wisecrackingly said, "Professor Durkin, get glasses," you know, because I'm squinting a little. But I've misplaced my bifocals. They will probably show up. They're probably on a doll somewhere in the toy room, knowing my children. So apologies if I have to do a little to get things going. I'll take these off. So when I add both of those equations together, I get delta E phasor vector dotted into the curl of delta H phasor vector minus delta H phasor vector dotted into the curl of delta E phasor vector. This is equal to j 2 pi f mu magnitude of delta H phasor vector, magnitude squared, plus, and here we could do something else if we really want to. We can add in the effects of conductivity. So if there is some free charge in the medium that allows conductivity, instead of just j 2 pi f epsilon times magnitude of delta E squared, I think the notes actually allow for a sigma to be added in there, minus j 2 pi f epsilon. And in fact, epsilon could be even complex if we really wanted to. You can go back and show that this proof will hold even if those conditions are true. let's go ahead and just leave conductivity in there, which kind of has the same effect at a given resonant frequency as complex permittivity, the imaginary part of a permittivity medium. Okay, now I'm going to apply a vector calculus identity. This guy here, that is hideously drawn, this guy here can actually be rewritten as minus the gradient of delta E phasor vector cross delta H phasor vector complex conjugate. And that's a really nice, elegant proof. And the best way to do this is if you've got about 15 minutes to kill at home or 20 minutes, go ahead and plug in this identity with actual values on X, Y, and Z. You know, just the basic identity using generic vectors. Cross it, take the divergence. You'll find you basically get the exact same expressions if you do it this way or this way. It's just a nice vector calculus identity. So we cross the two vectors, take the divergence. It's really the same as writing it out longhand. It's almost like a chain rule for this particular vector calculus operator. And it's very nice because it allows us to write this in a different format. When you apply this new vector identity, what I can do is say, okay, when this surface I'm going to take the volume integration of both sides of this equation. I'm going to basically integrate over the volume V, which is enclosed by S. I'm going to do that on both sides. I'm going to need like a volume element of integration dV. I don't even know if you can see that over there. Oh, I gotta be careful. dV. Okay. So my right-hand side becomes, and what I'm going to do here is I'm going to group some terms together. I have J 2 pi F. I got a J 2 pi F here. So I'm going to write this as J 2 pi F, the volume integral of the quantity mu magnitude delta H squared minus epsilon magnitude delta E squared dV. And then there's going to be this sigma term over here, plus the real value, sigma, integrated over the volume, magnitude squared, delta E squared, dV. So I'm just integrating each of these terms over the volume, and I'm grouping all of the imaginary terms that have a J with this in this term here, because all this stuff in here is real. And there's a J in front of it, so this is your imaginary term. And then the only real part that's left on the right-hand side is this portion right here, which is very important to the uniqueness theorem. This, on the other hand, I'm going to invoke a theorem in electromagnetics. Remember Gauss's law, which said that the divergence of a vector field, if you volume integrate it, is exactly the same as a surface integral of the flux of that vector coming out of the volume. We did that probably in electromagnetics and Physics 2 class and your junior level electromagnetics classes if you had Georgia Tech ECE 3025. We did that with E-field. because that's how you calculated charge, right? The charge density, the integral volume integral of the charge was equal to the flux of the E field, and we applied Gauss's law to go between the differential form of that relationship for E field and the differential form, or the integral form for E field. Here, we're using the exact same mathematical principle, but with a different set of vectors, this kind of weird cross product. So here we've got the cross product integrated over the closed surface according to Gauss's law. That is equal to delta E cross into delta H complex conjugate dotted into dn. So dn is a differential element of integration that slides around over the surface integral, or the surface across the area described for that surface, picking up just the normal contribution of that field solution coming out of the volume. So let's take a look at this here. What have we learned? If I have a little bit of loss over here, well, before we even do that, let's take a look at here. If the tangential component of electric field is specified on the surface of this problem, forcing delta E on the surface to go to 0, or the tangential component of magnetic field is specified on this surface, forcing delta H to go to 0 on the surface, or some combination of those is, then the dot product normal of this product is going to be 0. The reason is I've specified delta H, then delta H is going to be 0. Or if I've specified delta E on the surface, then this port is going to be 0. So if one of these is specified, then 0 cross into anything else is going to be the 0 vector. And if I integrate it across the surface, I get 0. So if you know the boundary of either E or H, this is going to be equal to 0. Now remember, that's only something we said about the surface, the behavior of those fields on the surface. That doesn't specify anything, at least not yet, about the solution within the fields. Delta H and delta E still could differ, could be non-zero from one another. But if it's a boundary volume problem, we're looking at the surface. We've specified those fields. Now, if we go over to here, we find that this must be equal to 0 within the volume. We're integrating across the entire volume, all of these fields. And look at this. If I have just a tiny, tiny smidgen of loss, sigma is 0.00000001 siemens per meter squared. Siemens per meter. Yeah. If that's non-zero, just a little bit of loss, then I don't have anything on the other side of this equation to counterbalance it. And this is purely imaginary. That means that the electric field difference between those solutions must be 0. Can't be anything else. So we've already shown now that delta E must be zero in the entire volume, because keep in mind, we're taking the magnitude squared and we're integrated over the entire volume. The only way to make that statement true here is to make it zero everywhere within the volume, which is what we tried to do. That's part of having a unique solution. If delta E is zero, then when I go over to the second term, this imaginary grouping, this term must be zero. We've already determined that. And what I'm left with is, again, a volume integration of delta H that, in order to produce the matching zero on the other side of the equation, must be zero throughout the entire volume, because you can only pick up positive contributions of that. And if you pick up even a smidgen of positive contribution with the H field, with the delta H field within that volume, you'll violate the equation. So that proves that delta H must be equal to zero as well. So this is interesting. This means that if I have even the tiniest bit of loss, I'm going to have a unique solution in electromagnetics. Only if you have a tiny bit of loss will you be able to have a unique solution. And that's a nuance that we have to be very, very careful of. And a nice example of that, I'm going to put on the board as sort of a counter example to show when the uniqueness theorem breaks down. You will always see papers. There's one that we reviewed like 20 years ago, somebody attempting to prove the uniqueness theorem in regions without loss. Can't be done because it's a very important condition for uniqueness. And I'll show you a counter example for that. Let's say that we define a region in space that we want to solve Maxwell's equations over. It is a very long, infinite, really, slice of space. So we're going to look at the solution in a box. And we're going to let the edges of this rectangular box go to infinity in the top and bottom directions. With x with the right-handed coordinate, y will go into the board, x will go that way, which means z has to go up there. So it's infinite in the z direction, and I'm going to specify the tangential fields E and H across this facet and this facet. So this would be infinite in both z and y. There would be some separation distance d, and then there would be another plate over here, which I'm going to let go to infinity in z and y, and that should identify a bounding surface, which all the way up at infinity, there's a little nominal connection, and all the way down at minus infinity, there's a little nominal connection across there. But basically, the field is going to be specified over this boundary region. So that's my A, and V is inside, or what we call S in the original proof. My bounding surface, volume inside. So this has some sort of solution, E and H, based on whatever sources that I've put in. Maybe I sprinkle a little bit of magnetic current in there. Maybe I threw in some electric field or electric current that's radiating in the system. Now, it turns out for this particular example, if there is no loss, there is always a solution that I can add that's Maxwellian that solves your field in there, but makes zero field values everywhere along that surface. And if that's true, then I could add any linear combination of, we'll call it delta E. Delta H. I can add any linear combination of that particular solution and generate a new solution that satisfies Maxwell's equations, but does not obviously make the solution E and H unique. And the perfect counterexample in this is basically two plane waves that are interfering with each other. Let's say that D is equal to lambda over 2, right? What happens if I take two identical plane waves and I set them to travel? And let's say they are, for the sake of argument, Z-polarized. And I'm going to send one of them in the positive X direction and another one in this one. Give it just the right phasing as well. In the negative X direction. Well, okay, what does this look like? I've got two plane waves. We know from our previous classes, or maybe you can intuit, that this is going to create a standing wave interference pattern. Wave coming this way, exact same amplitude, wave going that way. I'm going to have peaks and nulls. Where's the first null going to be? It's going to be here at X equals to 0. If I put X equals to 0 in here, I basically get E naught minus E naught in the X hat direction, or in the Z hat direction. And this is the XB0, that's 1. The XB0, that's 1. Zero field right along here. If I move over to X equal to lambda over 2, what does that give when I evaluate the field? E naught, Z hat, and here I have basically EXB to the minus J, 2 pi over lambda, that's what free space wave number is, or what the wave number in medium is. And we're evaluating the X equal to lambda over 2. Those cancel, and so I have EXB to the minus J pi, minus 1. Now I go over here, I have minus my EXP, I have the same basic deal, J 2 pi over lambda times lambda over 2. 2's cancel, lambdas cancel. This is also going to be minus 1. Minus 1 minus a minus 1 is also 0. So all along this X equals lambda over 2 surface, my field is going to be 0. This satisfies Maxwell's equation. And let's call this delta E, because I can basically take this and add any linear combination of this and its corresponding H field solution and make another solution. So therefore, that's not unique. But it's interesting that as soon as I put that tiniest little bit of loss in here, I can no longer write that solution, and there's no way to make a non-unique solution by adding a resonant mode like that in this way. Very peculiar to think about. But even the tiniest bit of loss makes the solution unique. So you can see that in a lot of these problems, for all intents and practical purposes, uniqueness exists. We just can't add some of these resonant modes. You say, well, wait a second. Hold on a second, Professor Dargan. What if this was uniformly lossy and it just had a little bit of loss, right? And let's say that D was, wider than a wavelength, wider than lambda over 2. Couldn't I still treat this like a parallel plate waveguide? So now I'm going to rotate everything by 90 degrees and say, okay, I've got some width here, but it's not in cutoff. If this were a metallic waveguide, if I had a metal sheet here, I could have a solution that basically represented two plane waves interfering with each other, putting zero field here, and propagating with a little bit of loss in the forward direction. If this was even a tiny bit of a uniform lossy medium, couldn't I take the waveguide mode from here, rotate it, and stick it into the problem and add any linear combination of that? That would seem to violate the uniqueness theorem that we just proved. And of course, the answer to that is, well, wait a second, where is that wave coming from? It's coming from positive infinity, and it's got exponential decay on it. So by the time, it's sort of a bit of a mathematical artifact, but when you go and observe it down here in non-infinity, that wave will have extinguished itself because the source of that wave would conceivably be from outside or bounding volume. That's how we get around that. Basically, so that mode that I tried to sneakily add to whatever solution is going on in this region, which kind of looks like a metallic parallel plate waveguide mode in a lossy medium, would extinguish itself long before I got to the observable region where I'm constructing my solution. And that's true on both sides, right? Whether there could also be a wave coming from this direction, just turn the solution 90 degrees or minus 90 degrees. But it still would involve drawing in exogenous energy from infinity. However, if there was no loss, we could very much construct some realistic solutions that didn't involve energy from infinity that would allow you to add these resonant modes to your solution. So the crux of the lecture is, the point is, all electromagnetic solutions in the real world are unique because there's always just the tiniest bit of loss. However, if we're in the vacuum of free space and there is no loss, there are these peculiar resonant modes that you can add to your solution and make them non-unique. But it involves things like exogenous energy coming in from infinity and trying to make a standing wave, that sort of thing. There's actually another proof of uniqueness that you can do in the time domain. And instead of loss, it involves no stimulation before time equals to 0. So basically causal sources. And what's interesting is you can show uniqueness in that scenario too. We've done it for a time harmonic system. And even though those conditions don't seem to be the same, really what you're doing is by adding loss into a region, you're doing almost the same thing that you're doing by adding causality. You're not allowing resonant standing wave modes that started off at time equal to minus infinity and proceed without loss at a steady state to plus infinity. You're disallowing those types of elements in your solution. And if you can do that, you'll get a unique solution where nothing else can be added to it to also solve Maxwell's equations.